Hello everyone. So welcome to week 3 live session by myself Anu, PMRF PhD scholar at IIT Hyderabad. So from the last class we saw that how MATLAB is very helpful and basic commands of the MATLAB, and then we also saw how can we use MATLAB to solve the linear algebra problems. Then we saw what is vectors, then matrices, and then we finally solved the assignment 2 solutions. Okay, so last class, I think there were not so many students, and this class also I'm not seeing so many students, so I can't wait. So I'm just starting. uh, this week basically was more tailored towards signals and system, and the basic operations, and that's what is a probability, and from there only the questions of week 3 um, we can see. So we will see what are the questions. First, we will see the questions are related to FFT. Then some questions are related to sample space, probability distribution, and the lectures are very good. So you can see the lectures. Then you can watch my lecture to have the more understanding. So before jumping directly towards the solutions, so I would like you to, we will first go through the concepts. So then we will go through the concepts. Screen is not changing. I don't know why. Um, Give me a second. Why my screen is not sharing? Okay. So we will first go through the probability basics. Then, okay. So basics, as we know what is probability. So the probability of any event A is defined without any actual experiment. So we can say the number of outcomes that is favorable to that event and total number of possible outcomes. That is a division. That is only the probability. But what if we have infinite number of events? So in that case, the limit n tends to infinity will be there. Okay, if we have finite number of events, then it will not be this case. But if you have infinite number of events, then limit n tends to infinite. We will see, yeah. So we generally do this relative frequency definition. This is the probability of any event A is defined as limit n tends to infinity. The number of occurrences of the event that is favorable to A, or we can say the A, or n is the total number of trials. So this is a basic definition. But for any experiment, you have number of outcomes. So that outcomes can be, for example, if you toss a coin, you can have the outcome, two outcomes, head and tail. Similarly, if you toss a dice, you have six outcomes, one, two, three, four, five, six, like that. Okay, so there are two set operations that is defined over probability, that is A union B or A intersection B. So A union B means all the events that is belonging to A plus all the elements that is belonging to B. Whereas A intersection B means all the events that is intersect that is common for A and B are the A intersection B. So these things we all know. We can see this graphically also. This is the common elements. This is all the same elements, and this A complement means all the elements that is not part of A will be A complement. So all these things we know. Now we have three properties or axioms of probability, which is first one is P of A should be greater than or equal to 0, or P of sample space equals to 1, or when the probability of the whole set is unity, or and P of A intersection B is if it is empty, then we can say P of A union B is equals to P of A plus P of B, because P of A union B has this formula, P of A plus P of B minus P of A intersection B. Now the question arises, what is mutually exclusive and independent elements? Okay. So if I am asking what is mutually exclusive and independent events, so sometimes we get confused. Events. Even two elements. What does this mean? So if we want to see it graphically, then mutually exclusive events look like this. A, B. But the independent events looks like B. So here we can see that if we take the case for mutually exclusive events, then the occurrence of A restricts the occurrence of B because both are lying in the same sample space. Okay. But in case of independent events, the occurrence of A doesn't depend or doesn't affect in any way to the occurrence of B. Okay. So what does this mean here? If we want to see it in mathematically, so P of A intersection B is equals to P of A intersection B is equals to P of A multiplication with P of B. This is the basic formula for independent events. Okay. And if we see this P of A intersection B, it is equals to 0 because P of A intersection B is 5. Okay. Now, if you want to see some examples, okay. So the probability, if we calculate, if we toss a coin and it is a random experiment and it has two faces, head and tail. So if we see the probability for occurrence of H or a head, then it will be the occurrence of head will restrict the occurrence of tail. So that's why head and tail, two events are actually mutually exclusive. Okay. Whereas if we have tossing a dice or tossing a coin, then that events will be independent events. Okay. So these are the different cases for mutually exclusive class. These are the two different sets for case of mutually exclusive and independent events. I hope this is clear to you. Okay. So whenever we talk about this one, P of A union P of B is equals to P of A plus P of B. This implies A and B are mutually exclusive events. So sometimes we often get confused between these two events. So my aim was to tell you. Okay, so previously I was defining what is probability. So one more thing, a very little brief concept about probability theory. The probability theory is defined for this particular thing. This is a measurable space, which has three main components. Okay, this is big omega, this is F, and this is P. Okay, so as we defined probability previously, but this big omega is a collection of all the sets. This F is the field that defines on the subsets of the elements of F, this big omega, and P is the probability that will be assigned to the elements or subsets of big omega. So what does this mean? Fields follows three particular properties. That is not very important for this particular course because this is the course for MATLAB. But just remember that it has three properties that you can refer to the internet also, or I can tell you that even if A elements belongs to field, then A complement will also belongs to field. Okay, and if A union B belongs to field, then this means that A union B union all the elements belongs to field if or elements are if the events are disjoints. Events are disjoint. If you have doubt, you can ask me. So these are some properties. Okay. So if based on these two properties also, if A and B belongs to field, then this implies that A intersection B also belongs to field. So these A and B are the subsets of the elements of the omega. Okay, omega is what? A set of all the outcomes of a particular event. Okay, that is the random experiment. So this is a probability theory that is also known as measurable space. Okay, omega FP. So yeah, now we will go to the random variables. What is random variable? Like sir also taught in the class, random variables. So I'm giving you some different intuition from that, what sir taught. Okay, so as we know, the random variable. So from the name itself, we can see that we are giving the name as variable. Okay, and that is also random. So we often get confused like how to remember this. So since this is random, so it will be defined for random experiment. But it is not only a variable; it is actually a function. Okay, so we have to see from this perspective. The random variable is a mapping or the function from the outcome of any random experiment to the real life. Okay, so this is what it is. So this variable assigns the outcome of any random experiments to a real line. Okay, the real line have various values from minus infinity to plus infinity. In fact, it has infinite number of values. So it can assign any real number to the variable. Now we will see from the example. Okay, so if we have, since I told you this is a function. So what is function? It can have, it can have what? Many to one or one to many. You can have it's a homework like you check many to one is possible or one to many is possible. Okay, so one of these will not be possible. So I will ask you in the next class, like which one will be possible. So we cannot assign, okay, one of these two conditions. Okay, we cannot assign the single outcome to different values. Okay, we can assign the same value to the different outcome. Okay, so I think this is possible, this is not possible, but you have to check and let me know. Okay, so this is one of the case. But yeah, I was telling, since it is a function, the function in what perspective? You have outcome set. Okay, this is one, that is domain. I'm telling you in perspective of function. And this is what? Range. Okay. Okay. Now you have capital omega. Okay, big omega, which includes sets of outcome of any random experiment, W1, W2 to Wn. So the single element of outcome set we denote it by small w. Okay, that is omega. Now these are W1, W2 to Wn. Okay, now we are assigning real values. Suppose we are assigning 1, 2, or some value to 3. Okay, some way of mapping will be there. So this mapping, we are giving the name as X, which is random variable. Okay, that's why we give, suppose this, we have omega as H and T. So we give H of X of H is 1, x of t is -1. Similarly, if we have omega dash as 1, 2, 6, so we give x of 1 to suppose -1, we can give x of 2 to some any real value we can give 8 or something, but it should be relatable that it will be ease our solution or problem formulation. Okay, so why we are doing, because we can't deal with the actual outcome of any random experiment, so we assign that outcome to the real line values. Okay, so this is what the random variable, but there is one trick, like, but what if we assign all the continuous random continuous outcomes? Suppose these are the discrete outcomes. So do you think that we can assign all the continuous outcomes of any random experiment to any real line numbers? Do you think that is it possible? Think about it. So this is a question, like we cannot assign. So in that case, we assign the subset of the continuous random variable output to a finite numbers, to a finite output. We assign in that way. That is also called Borel set. Okay. So, but that these things are not covered in the class, so I'm just leaving these things. Okay. Now we will go to the Bayes theorem. That is very important in our case, because so since I was telling about this thing, um, this F, say, this big omega Fp composed of non-empty set omega of elementary events, then sigma field of the subsets of the all elements, and the probability measure P on the sets in F. So we cannot give probability to all the events, but we can only give probability or assign the probability to only the elements of the sigma field. So that is a field F. Okay. And the F has this properties that I told you. So I think it should be clear to you. But even if you want, you can refer to the probability theory, but that is not necessary for the course that we are dealing to. Okay. So I will tell you some examples for Bayes theorem, which is very, very important. So first I will explain you what is Bayes theorem. Then I will tell some examples for the Bayes theorem. So basically Bayes theorem. What is Bayes theorem? So that was a major coverage in the class. So suppose you have, as I told you, what is mutually exclusive events. So this is important in this case. Suppose you have AN mutually exclusive events. AN means A1, A2, to AN. So if we have mutually exclusive events, so it will not have any common part. Okay, I think you will support this. So A1, A2, A3, it will not have common part till on AN. These are mutually exclusive, as I told. Okay. Now P of A, if you want to write this is A, overall A, how can you write? P of A intersection A1 plus P of A intersection A2, so on, P of A intersection AN. You can write in this way. What I am telling, like what is a common part from A1, A2, AN? You are writing in this way and you are summing it up and you are giving the name P of A. I think up to this point we are clear. Okay, if you have any doubt, you can ask. Now we have the property of P of conditional probability. So conditional probability is very important. P of A by B. We know property. Conditional probability. Okay. P of A by B is what? P of A intersection B is equals to P of B. It means that what is the probability for the occurrence of event A given that the event B is already known? Okay, so this is what. Now, if I write P of A intersection B is equals to what? P of A by B into P of B. I can write like this. Agree? Now, equation number 1. Going from equation number 1 to equation number 2, taking some different colors. Let's take pink. From 1, we can write P of A is equals to, now this we have to write like this. P of A by A1 into P of A1. Okay. P of A by A2, P of A2. So on, P of A by AN into P of AN. So this is what the Bayes theorem says. Okay, you have multiple events, okay, from A1 to AN, which are mutually exclusive to each other, so that if they are not mutually exclusive, we cannot write like this. Okay, first is the first this expression only. Okay, once we write like this, then you how can you compute based on their mutually exclusive events, and how will you calculate probability of occurrence of A? Now the question arises, if we have, suppose you are asked to calculate P of A divided by this one. So how will you calculate? Let's go by the formula. P of A1 intersection A divided by P of A. So this is what? P of A by A1 and P of A1 divided by P of, we have to write like this. P of A by A1 plus multiplication by P of A1 plus P of A by A2 multiplication of P of A2. So on P of A by AN multiplication P of AN. So this was what another equation for Bayes theorem. So these two formulas are very, very important, and they are asked. I never forget these formulas. I can derive at any point of time because I know the basic from where it is coming. Okay, what is the basic conditions, and where from where I'm calculating P of A, and from where we have to calculate P of A1 by A, like this. Okay, so these equations are very, very important. Okay, now where these base equations are used, this is our main objective. Okay, so sir taught this in the class also, but I don't think that this particular derivation was covered. So this derivation, we can see how these are calculated. Okay, now if we have, suppose, two bags. Okay, now two bags, you have to choose one red ball. So I'm giving you the scenario. Let's have the utilization of this base tool. So you have two bags. Sorry, let's make it the proper way. Bag 1. Second bag is bag 2. Now you have two different type of balls. This is the red ball. You have, suppose, three yellow balls, and you have here as 5 yellow balls. Okay, and suppose you have, next is green. You have uh, 2 green balls, and you have 3 green balls. Okay, you have two conditions. Okay, bag 1 and bag 2. Let's have this as experiment bag 1 and bag 2. Now the event is defined A as selecting yellow ball. Okay, selecting yellow ball. Now the question is, given two bags as above, also yellow ball was chosen, calculate the probability that the yellow ball chosen from bag 2, let's say. You have to calculate this. So let's first understand this problem. Okay. So we have two bags, bag 1 and bag 2. Since they are in the same sample space, but they are different. So we can say that they are mutually exclusive at the same time. So you have, suppose B1 and B2 are two mutually exclusive events. And in that you have to calculate the yellow bag. So A is a probability of drawing the yellow bag. Okay. So now choosing bag 1 and bag 2, I will write answer in this color. Okay. So answer or the solution approach. Okay. So probability of B1 is 1 by 2. Also, probability of B2 is 1 by 2. So that's why the fundamental of P of B union B is equals to P of B1 plus P of B2. And this P of B union B is nothing but this one. So equals to 1. So it is satisfying this. So let's, okay. This is also mutually exclusive at the same time. Now, you are asked P of B, P of A, selecting yellow ball. So we know that selecting yellow ball is what? P of A. P of A given probability of selecting yellow ball when the bag is B1. Okay, multiplication with P of B1 plus probability of selecting yellow ball when the bag is B2 and B2. This is from the base theorem as we know. Okay, let's calculate this. P of A by B1. We are going very slowly. Okay, you have any doubt, you can stop me anytime. A by B1. So 3 by 5. Agree? P of A by B2 is what? P of 5 by 8. Agree? Now let's calculate P of A. So this is 3 by 5 to 1 by 2 plus 5 by 8 into 1 by 2. So I can take 1 by 2 as common. 3 by 5 plus 5 by 8 is equals to 1 by 2. 40, 24 plus 25. Just giving you 40, somewhere 14. Okay. Now you are asked, given the probability was from yellow ball, from which bag it is asked? Bag 2. So it is asked, what is probability of B2 given A? It is asked. This is asked. You can again read the question. Calculate the probability that the yellow ball chosen from the bag 2. It is asked like this. So we know that probability of B2 by A is what? P of A by B2 into probability of B2 divided by P of A. Agree? I hope you are agree. Now, we know P of A by B2 is what? 5 by 8. This is 1 by 2. And this is 1 by 2 from this one. 49 by 40. This 1 by 2, 1 by 2 get cancelled. Here 5 by 8 into 40 by 49. And we can calculate. We'll definitely get something. 8 5 to 40, 25 by 49. So this is how the Bayes theorem is utilized. And I think the week 3 was basically based on the concepts. MATLAB was not used, so that's why I'm not showing you the MATLAB. But I can also show you the MATLAB have the background for the MATLAB. I can show you. But as far as the week 3 is concerned, so Bayes theorem was used. So we also solved some of the problem based on this. So here I gave some basic example utilizing the Bayes theorem. You can have multiple questions. You can be asked what is the probability of choosing the yellow ball. Okay, so you have to answer P of A. So similarly, you can have multiple bags or you can have multiple scenarios. Then choosing one scenario, what is the probability of getting particular thing, and if that particular thing is we have that, and what is the probability of of getting from the scenarios, suppose C1 or C2, like that. So this can be asked in multiple forms. So I hope basic theorem is clear to you. Now we will move to the next topic of the weekly, which was discussed in the class. So again, I'm giving you some intuition like what we saw from the starting of the class, because I think uh, Pala Marti joined late, little late. So first we saw what is probability, how the probability is defined. Then we saw the measurable space, which was not covered in the class, but I just gave you the intuition. So if you have the further interest in that, you can check the Pillai notes. It's very good for probability. Then we saw what is the difference between mutually independent events, mutually exclusive events, and the independence event. These are often used interchangeably, but it is not at all correct, and it is very difference between these two events. And yes, so we finally saw the base theorem. Now again, I'm moving ahead with another question. If you want, I can take some other question. So yes, I think it is not required. But yeah, remember one thing, but for independence event P of A intersection B, it is P of A into P of B. But for mutually exclusive events, P of A intersection B is always 0. Okay. Now, okay, this is very good question. It's a similar question also. So example 1.2. So, I don't know whether you will solve or not, but yeah, I will solve for you. So example 1.2 states that a box contains 6 white and 4 black balls. Okay. Remove 2 balls at random without replacement. What is the probability that the first one is white and second one is black? So again, let's have this. Uh, let's again understand this. A box, one box is there. It contains 6 white and 4 black balls. Removing the 2 balls at random without replacement. So without replacement means you are not replacing it. Okay. So what is the probability that the first one is white and the second one is black? Okay. So we have to solve using base theorem. Any idea how to approach this? Okay, let's see the solution approach. So suppose let's take two events, W1. The first ball removed is white and the second ball removed is black, W1, B2. Okay. So we have P of W1 intersection B2, which is because these are independent events. Because anyway, you are removing white or and the second one remove the black. These are independent events, so that's why these are the multiplication of these two. We can actually say so using the conditional probability. Uh, Probability of W1 B2 is equals to probability of B2 W1, which is equals to uh probability. Sorry, this is not mutually exclusive. Sorry. So again, P of B2 by W1 is equals to P of W1. Again, going to the conditional probability uh, function. This is rule by conditional probability. So P of W1 B2 is equals to P of W1 intersection B2 divided by P of W1. Okay. So P of W1, as we know, what will the probability for first ball removed is white, since uh we have the ball is 6 white and 4 black. So 6 by 10 will be definitely the probability of removing the first one is white. Okay, so that's why P of sec W1 is equals to 3 by 5. When it's actually removed, then we have the less number of balls, and because it is not again placed, so it is without replacement. You are not replacing again. Okay, so this is like P of W2 given W1. So P of second ball removed is black. So black we have only 4. Okay. But the number of white balls has been reduced because it is not replacing again. So it is 4, 5 plus 4, it is 4/9. Okay. Now you are asked what is the probability the first one is white and second one is black. So this is what it is asked, like first one is black, white, followed by black. So this should be intersection. Okay. So again, this will be, since this is an independent image, so directly it will be multiplied. So here you are not utilizing base theorem because it is not asking, like it doesn't seems to utilize the base theorem at all. So like this type of question you have to solve by basic intuition. Like first of all, what it is asked. So first it is asked like the first one is white. So let's take that as the first event. The second one is black. So let's take that as second event. Now let's see whether these two events are independent or not. So as these two events are independent, so these are directly multiplied. Okay, because it is not affecting others. White and black, it is not affecting others. But if it even it is black, so it can affect. Okay, so we can directly multiply and we can have this solution. So this is the 0.25. Okay, so I hope this is clear. So we have covered one question based on the basic probability. So yeah. So if you have any doubt, you can ask any question. Let's say this question. Two boxes. Okay. Two boxes B1 and B2 contains 100 and 200 light bulbs respectively. Now the first box B1 has 15 defective bulbs and a second have 5. Suppose a box is selected at random and one bulb is picked out. What is the probability that it is defective? So we have to again calculate P of A. It's simple. How will you calculate? You have to calculate P of A by, means if we assume that the event A is a bulb that defective, P of B1 you have to calculate A by B1, P of A by B2. Then again using P of A is equals to P of A intersection B1 plus P of A intersection B2. That is equals to P of A by B1 into P of B1 plus P of A by B2 into P of B2. Let's see how this is solved. So again, I told this instead of A, they have considered defective bulb is picked out. So P of D by B1, P of D by B2. It is calculated. Sure. Now, since the box is selected at random, they are equally likely. So P of B1 equals to P of B2 is equals to 1 by 2. And P of D is nothing but P of this particular base theorem formula. So now there is a 9% probability that the bulb is picked at random is defective. Okay. Now, suppose we test the bulb, it is found to be defective. What is the probability that it came from the box 1? So again, the base theorem. Okay, P of what it asks, P of B1 given defective. Okay, P of B1 given D, P of B1 given D. So it is asked like this. So again, this is the formula. It is calculated. Okay. So as I was telling that what is independent. So events A and B are independent if this is follows. So this is easy to show that the independent event implies that these are also independent pairs. So we can say these things also. So these are not important for your perspective. I also told that what is the random variable. So from random variable, if it's some experiments are there, I will tell you. So from probability perspective, these are only covered. Random variable, I'm telling you. Like, yeah, this is very important. So let omega f(p) be a probability model for an experiment and x a function that maps every outcome that belongs to this omega to a unique point in R. So as I was telling, like whether many to one or one to many will possible or not. So unique point in R. So you can't map like this. Same output to different numbers. You can't map. So this is a defect here. So many to one is possible, but two to are not a single output. So because it is a unique, it should be unique. Because there is a logic in this. Why unique? I'm telling you. So because if you determine inverse, it should belongs to the outcomes output space of that particular random variable. So this big omega. The inverse of this x should also belongs to that omega. Okay, so that is why it is unique elements. So since the outcome is not certain, so is the value is this one. So if B is some subset of R, like if we have some B, we may want to determine the probability of X of omega belongs to B. This is zeta belongs to B. To determine this probability, we can look at the set A is equals to X inverse B that is belong to omega, big omega. That contains all zeta that belongs to omega that maps into B under the function of X. So we can see here, okay. So if the set A is equals to, let me take some light color. If the set A is equals to X inverse B also belongs to the associated field, then it is an event and the probability of A is well defined in that case. So we have to make sure X of zeta belongs to B, which is equals to X of inverse of B. So B, we are defining B as what? We're defining B as what? B as subset of R, some subset of R that we are considering for mapping from the output space of capital omega to real line. So that is a B. That is a range we can see. So if we keep X inverse of B, so it should belongs to X of zeta. Okay, I hope this is clear. So we can see from here also, suppose you have this omega and omega have all the elements of output of the random experiment. Let's say A. So output of random experiments A, which is we are keeping that, we are mapping that to any real line. That is X, let's say 1, 2, 3 or any value. But the outcome, if we see some subset, okay, if we see some subset, then if we say if B is some subset of R, we may also want to determine the probability of X of zeta belongs to B. We want to have. What is this? We want to have, suppose. So in that case, X of inverse, like if we say X, suppose this X goes here, zeta equals to, suppose zeta is here, this equals to X of inverse B. Since X of zeta belongs to B, so X of zeta should belongs to, so X of inverse of B should belongs to omega, isn't it? It should belongs. And this is also some set, so it should belongs to omega. So this is what we are making sure. And this statement is what it is made for. Okay, so if that is B, then X inverse of that should also belongs to X of big omega. Okay, so this will also be associated with field. We are stating that if it is determined, if we are assigning some measurable space, that is big omega F P, then if B is some set belongs to F, then A is also some set belongs to F. So F is nothing but the field of the sigma field where we are having the operations on the subsets of the elements of capital omega. And for that subsets of elements only, subsets of sets only, we can have the probability measure. Otherwise, for others, we can't have the probability measure. Okay, for that case only we are defining this omega FP, and that is not for as important for your course. But yeah, okay, fine. So the probability of the event that is belong to B is equals to P of X inverse, P of X inverse of B. Now, however, X of inverse of B may not always belongs to F for all B, thus creating difficulties. The notion of random variable makes sure that inverse mapping always result in an event, so that we are able to determine the probability for any B belongs to R. So inverse move mapping is always available. So one more question is, like, can we have, what do you think? Can we have many to one or one to one many mapping in case of function? So will that be a function? Think about it. So what is my question is, uh, like, what do you think? can we assign all the variables or this all the variables to a single value? Do you think that can we assign head and tail to a same value in the in real axis? Do you think? So yes, in case of function, we can have many to one, but one to many is not possible in case of function. Um, in that case, that is not a function at all. So that's why random variable, you can have many to one, but one to many is not possible. Like head is uh, also referred as one or minus one. No, that is not possible. But head and tail can have one value. This is possible in case of function definition. So that's why the random variable mapping is named as a function. And like, what is it? What is uh, what is the difference? Like, why it is not possible? Because a single element in the domain set cannot have a different images in the codomain set. Okay, so thus there's no such function known as one to many. Okay, so one to many is not possible as a function itself. So you remember this. I used to have this doubt. That's why I considering this. Okay. Now, PMF, PDF, and their properties is considered covered in the class of week 3. So I will also cover. Give me a second. Okay. So suppose you have now random variable. Now random variable can also have some properties. So we define 3 basic type of functions over it, or distribution. We call it as a distribution. Now you understood what is random variable. Now you have probability, mass function, probability, density function, cumulative density function. So this is called PMF. This is called BDF. This is called CDF. Okay. So as we can see, a random variable can have the discrete outputs, right? So similarly, random variable is defined, can be defined as continuous or discrete. So random variable is bifurcated into 2 parts, discrete and continuous. So discrete and continuous in this sense is random variable can be discrete. We will see. I think that is not covered in the class, but both are the discrete random variables and the continuous. That will be covered, I think, in week 4. But yeah, what is discrete and continuous? So discrete means it will have the actual numeric values, and continuous means it will have the subset of values. You cannot define the one value. You will have some subset from 0.2 to 0.3 like that. You will have the subset. Okay, so these are discrete and continuous. Now, this PMF, okay, this is actually it is defined as P of X equals to Xi. Okay, this is PMF. That's probability mass function. So if we have random variable, we will have random variable suppose X. So this is defined as PMF or P of X equals to Xi. Suppose you have their random variables take suppose 3, 4 values. Suppose it takes 1 value, 2 value, or 3 value. So the what is the probability that your random variable X takes the value 1 is 0.5 suppose. This value is, what is the probability that your random variable X takes as 2? So suppose 0.75. So what is the random variable that random variable your X takes value 3? Suppose it is 0.25. Okay, so this is basically the probability that a random variable takes, but it is defined only for discrete random variable. Remember this. Because since I have discrete values, okay? Discrete random variables. Now, the second one is PDF. Okay, so before defining PDF, I will define CDF. So let's first define CDF for CDF is only defined for discrete random variable. For discrete random. So CDF of x of x. So that's why PMF is also defined capital X here. Okay. So it can be written as P of x of small x. Okay. Which is equals to this one. Okay. This is the basic formula. Please remember this for PMF. Okay. Small of x for discrete random plus xi. P of x equals to xi. This is a summation starting from taking from any random variables. What is the probability for taking all the values? Their sum. Okay, that is called CDF for discrete random variable. Whereas CDF for continuous random variable is what? PF of x is equals to integration of minus infinity here x less than equals to xi or minus infinity to xi p f of x. Okay, dx. So this is what this is called PDF. So this is probability density function for continuous random variable. This is PMF for discrete random variable. So what did you observe? So if we're calculating CDF, which is a cumulative distribution function, it can have two types, discrete random variable and continuous random variable. So for discrete random variable, you will have the sum till particular value that you want. So you want f of xi. So you are only keeping all the x less than equals to xi, summation p of x equals to xi. Okay, that is PMN. Now if you have the continuous random variable, so you will have minus infinity, all the summation from minus infinity to fx. Okay, so this f of x, if you do the vice versa, so what it is? F of x equals to d of dx, f of x. So why this is not a discrete value? Because you cannot have a single value for any single value in the output set. Okay, you cannot have because it is a continuous value. We will understand again. So what does this mean? This means that f of x plus delta x minus f of x divided by delta x limit delta x tends to infinity, tends to 0. You are agree? This is the basic definition for the differentiation. Okay. Now, okay, this means, okay. So if we plot f of x, small f of x, we plot all x. So if you want to have this value or this value, this is suppose x1, this is x2. This is capital X that takes the value small x1, x2, xd, xn. Okay. These are the random variable value. So their value, suppose it is defined this value. So this value, this value. So if you have, so we cannot assign. So what will the value for f of x, suppose it is asked? What will be the value for this? So it is defined as 0 because you cannot define that value. But if it is asked for a set of x less than x1, 2x1, x2, it is some value. Some suppose a. This is a. So it can only define for some small set, but it cannot be point. We cannot define for point. So that is a limitation for continuous PMF, that is also known as probability density function for the continuous random variable. Okay. Now, this is PMF and PDF, and this is also equals to f of x less than equals to x. Okay. So this is CDF. So what is the physical significance of CDF and what is the significant significance of PMF and PDF? So as we know, PMF and PDF shows that probability, that is assigned probability for a random variable to have the particular value. Okay. In case of discrete, it is PMF. In case of continuous, it is PDF. Okay. Now, what does this mean for continuous random variable? The speed CDF. Why it is required? What do you think? If you already have probability value, so why CDF is required? It's just the integration, right? From all the minus value to the plus particular value, it is a CDF. So why it is required? Can you have, let's have this figure, then we will see. But think about it, why it is required. So from the formula, we can see the cumulative distribution function gives the probability that the random variable is less than or equal to x. Okay. It is showing less than or equals to x. So what does this mean? So if you have the particular value, if you have f of suppose 3, okay, if you have f of 3, so it is showing probability, sum of all the probability from x less than equals to 3, p of x less than equals to 3, isn't it? So it is showing the integration part. So that's why what will the probability for p of big omega? What do you think? What will the what will the value of f of big omega? What do you think? It is equals to probability of less than equals to all the elements of omega. So what does it mean? It should be 1, right? So that's why the maximum value that the CDF holds is 1. Okay. Now what do you think? Now it is, since it is a sum. So what do you think? It will be what will be the nature of it? Will it be increasing, decreasing, or what? Constant, what? Since it is a sum, it is only adding the probability that a random variable takes. It will be non-decreasing. Don't you think? It will be non-decreasing. It will be non-decreasing. When it is increasing. Why non-decreasing, I'm telling? Because it can have the value 0. Okay. Now it will start from 0, or it can have value. It is not guaranteed, but it is not decreasing in nature, or the monotonous in nature. Okay. So this is what the probability density function means. Also, why we do this CDF calculation and PDF calculation? Uh, what do you think? Like, so it is often used for the statistics because the cumulative distribution function is given by P of x less than or equals to x, which shows with what rate the function has been increased, the slope, which is the probability actual slope. If you have, suppose what I'm telling, CDF curve, just P of x, this is small x, and I'm telling this is like this. If you have the slope, okay, so what do you think? The slope should be high or low? It should be steep, or it should, what should be the slope? What do you think? So basic thing is the slope itself is showing d by dx, because slope is what? Rate of change in y divided by the rate of change in x. So slope is nothing but, which we say tangent is m. Suppose this is m. Del y by del x is nothing but of f of x. Okay. And it has certain properties. Okay. It has certain properties. It is non-decreasing in nature, and also it will lie, the value of f of x of infinity is equals to 1, f of x of minus infinity is equals to 0, and the value lies uh, f of that is, we can say this word I can write like this: limit of x tends to minus infinity, f of x is equals to 0, and I can write limit of x tends to plus infinity, f of x is equals to 1. And it is continuous, non-decreasing, because f is non-negative. Okay, these are the basic principle, like why it is used. And I will tell you the basic example also, like where we often use it. Give me 1 second. Okay, so I have covered basically these things. Now, non-increasing and decreasing. Now we can move towards additional property of CDF and PDF we can have. Now, one more important property is, I would like to tell you. Just forgetting. Now, if it is asked P of X, X1, X2 is equals to, this is equals to F of X2 minus F of X, X1, X2 minus F of X, X2. Okay. But if I'm asking X1, X2, so it is equals to F of X2 minus F of X1 plus F of X1. Sorry, P of X1. Okay. So this is very important. You please make sure that here the equal sign is not there. Okay. If you add equal sign, you have to add probability at the same time. Okay. And it is also, we can also write like this. We can now have this X1 to X2 F of capital X small s. So this is equals to P of X1 X X2. So these are covered in the class. Like if it is asked, you can have. So I was giving you some example, like what is the significance and all. So since probability density function and the community density distribution function, so here you understand the difference. We are talking density and it is a distribution for CDF. Okay. Density in case of PDF and distribution in case of CDF. I will tell you the difference why. Which is a very fundamental concepts, basically in statistics, probability, and often in my research, I use it very often. So why it is important? So this PDF, it describes the likelihood or the probability that the continuous random variable takes on a particular value. As I was telling, that what is the probability it takes the value. So this is, I'm talking in case of continuous random variable. You can also have the similar case for discrete. So this PDF is non-negative for all us, and the total area and the PDF curve is also 1. That is one of the very important property. You can have the problems related to it. Okay, the PDF significance, we are first talking about the PDF significance. So the total area also, it is 1. You understand that. The PDF helps in understanding the distribution of the continuous random variable. While the nature of the PDF at a significant point does not represent the probability, because it has the probability for a particular interval. It doesn't have the value, okay? As it can be 0 or less than 1. So the area under the curve over an interval gives a probability that the variable range falls into within that range. So that's why the particular range, okay, if we have the integration, it shows that the value for the probability. We can also only have the probability for a particular range. We cannot define for a particular single value. Okay, so let's take some example. So if we have the example, the height of, suppose, the adult woman or men, in a certain population, which can be modeled as a normal distribution as we have. Okay. The PDF might look like a bell curve centered out on the average height because it will bifurcate or distribute into two part, okay, in an equal part at the average. Okay. And if you want to have the probability that a given selected random band is less than or between some certain value, okay, you have to integrate over these two values using this particular formula because we are talking about PDF. So in that way, it is very helpful to calculate the area. We have to calculate the area under the PDF curve between those two heights. If you want to have the height between suppose 5'8" to 6 feet for adult men, so we have to calculate the actual area between these two. Okay, in the PDF. This is the significance for PDF. Now coming to the CDF. So these CDF gives a probability that a given random variable val x will take the value less than or equals to x, which can be defined as f of x equals to p of x less than or equals to x. Agree? Okay. Now what is the significance? The significance provides a complete description of the probability distribution of a random variable. How the complete description? Because it allows for the easy calculation of the probability over the intervals. Okay. And helps in determining the percentile and quantiles. Let's say we have suppose the same example that we have. If you want to know the probability that a given selected band is less than or shorter than suppose 510, you can have the value of f 510. Then it shows all the probability that the given band has the height less than or equals to 510. Okay. So suppose it have the value, suppose 0.6. So this means that 60% chance that the randomly selected man from this population is shorter than 510. Okay. So this is the significance of PDF and CDF, and this is very important in real life. That is, we can have quality control, we can have finance. So quality control in perspective, like suppose in manufacturing, the companies often use PDF and CDFs to model the variations in product descriptions and so suppose length and weights. Understanding this distribution will ensure the product whether the product is meeting the quality or not. Suppose in my research also I'm using these two curves very often, and also so these are some examples. So in conclusion, we can say that uh, the PDF and CDF are both essential tools for understanding and working with random variables in various fields, because the random variables are representing the basic natural phenomena. The random experiment can be anything. Okay, so the height, population, and the measuring any simple quantity can be a random experiment. Okay, because it is a random. So they provide very critical insights. Okay, so yeah, these are some basic examples. Now moving to the next part of the lectures that was covered as a part of week 3. So I think PDF, CDF, I have to remember that again, the transformation of random variable was covered for a very short time. So yeah, so the basic, again, using this only, we have to cover the transformation of random variable. So what does this mean? Suppose if y is random variable and x is a random variable. These are two random variables. Now suppose y is formed used by transforming x. So suppose what does this mean? This means that y is some function of x. Okay. Now x is given random variable. Now you have to find the function of random variable. Now since every random variable is described by PMF and CDF or PDF or CDF, since we are defined, suppose me as Anu I have defined by my name, my height, my qualification. Similarly, the random variable is defined by PDF and CDF. So again, we have to calculate the question mark is what is the CDF and PDF of y given the random variable x, because it's the function. So as we know, we'll go with simple formula, simple basic, because I don't want to remember the all those equations that was given. So let's say you have to find f of y, which is a CDF of random variable y. Okay, so this is what this is f of y less or equals to y. This is capital Y. this is what we know, that this capital Y is function of X. Okay. Now, since capital Y is X less than or equals to F inverse of small of Y. So this is what? This is what? Probability, sorry. Oh my God, this is probability. Yeah, I'm going with basic definitions. I got confused between F and P, so I'm taking some different color. Yeah. So I hope this is clear. This is capital P and this is P. This is what? This is what? This is, since this is X, so it will be X. Since this is this of Y, this is the F inverse of Y. Agree? So F of Y of capital Y, this capital Y, this is this. Okay. So if we have a given random variable X, so it will be like this. The CDF of Y will be represented in terms of like this, CDF of X. Now you are asked probability density function, that is a bit basic, like name is more important than other qualifications. First you know the name, then you will have this. So similarly for random variable also, you are asked to calculate capital P of Y. What is this? So we know that this is a F of X of F inverse of Y. Okay. So this is what we are having, F of, so since this is divided by F of Y, so you can have this formula only, and you can have this. But if you want to have closed form equation also, I'll tell you. Just a closed form equation. But we have to go like this only. So this is a closed form equation, because that will be d of, because it is divided by this, so d of X, d of Y. And since it is division, like it is a differentiation, this is small of X, and this is sorry, F inverse of Y. So what I'm doing, so this, I'm having the differentiation F of X by Y, D of X by Y, and multiplication with F of X, F of inverse of Y. So this is what PMF of Y, given you have the transformation of random variable. So yes, I think this is clear. This was covered in the class. Now we can move to the questions. Okay, and some Fourier transform, Fourier series was also covered in the class. So I will just have the notes for that also. So okay, I will tell you what is Fourier series and Fourier transform uh, by my notes itself. So these are some basics only we are just talking about. Then we will go to, so yeah, convolution was also covered. So I'll just tell you what is convolution. So the convolution is actually can be evaluated in different way. It is an actually the operation. It has many other useful. So suppose you have LTI system. So if we have input X T and YT as output, so the YT can be represented as XT convolution with HT. So HT is actually the transfer function. So here basically the convolution is used. So okay, so if we define convolution by basic function, so this if yt is asked like what is the formula for yt, so it is tau x tau ht minus tau t tau minus infinity to infinity. This is the formula for convolution in continuous domain, where from minus infinity to infinity tau equals to x tau multiplication with h n minus tau. This is a formula for n discrete time. So what does this mean? It's showing that the output of the LTI system, how will it varies? Okay. So suppose you have example as this particular thing. Let the rectangular pulse x of n equals to x of n minus x of n minus 10. Okay, you are having the impulse response of this. So this is a discrete system, let's say. So we have to determine this output as y of n. Okay, so how will this x of n looks like? So it will have values from 0 to 10, x of n. And h of n is actually this way, because 0.9 UFN. So if you go with the formula, which is what I told you, x of tau is x of n minus tau. So this x of tau, or we can say x of k. So x of k is nothing but 1 in all the case. Okay, of n minus k, or x of h of n minus k. N minus tau I'm telling, those it can be k. To n minus k is nothing but you are dividing n minus k from k is equals to 0 to n, where from wherever it is defining from minus infinity to infinity also, but it is defining from 0 to all the values for a 0 to n. So you can have these values, and it is showing like this y of n. Why it is only defining from 0 to n? Because all these values will be 0. So only having 0 to n. Or if you start from 0 to it will be n. If you start from 1, it will be 10, because you're only anyway you are having 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But every discrete value starts from 0. But in MATLAB it starts with 1. You remember this thing. So this is the basic principle for convolution. And what is correlation? Okay. So if it is asking the output of LTI system, then it is a convolution. If it is asking the similarity between two signals, then it is a correlation. The correlation convolution have two basic difference. I'll tell you. So if you have HT, XT, and YT, so YT is equals to HT convolution with XT. Okay. Now if you have XT and YTS, two signals, similarity between these two signals are as given by XT correlation with YT. And since we know the different formula for that, but here you will have X tau YT minus tau dt minus infinity to infinity. So, and whereas xt convolution with yt has this formula as minus infinity to infinity x tau yt minus tau t tau. Okay, so here we are integrating with respect to t, okay, and here we are integrating with respect to tau. So this is the formula difference between that, and the application is also very different. Okay, so if we have the similarity where which value it is collapsing and we are integrating over it, the signal values, then we are doing correlation. Whereas we are just reversing the signal and having the common part and we are integrating over it, then that is a convolution. Okay, now Fourier series, Fourier transform. So one question which arises in our mind is what is Fourier series and what is Fourier transform? But the only similarity between these two is the same scientists developed Fourier series and Fourier transform. Other than that, no similarity. The application of Fourier series is used in Fourier transform, but there is no similarity between Fourier series and Fourier transform. In what sense? Fourier series is the time domain representation of the signal, no, only periodic signal. So you are representing the periodic signal in the form of sum of sinusoid and non sinusoids. So that is the Fourier series. Okay, it is the only time domain representation first of all. Okay, and it is only defined for periodic signal. So this is Fourier series. But what is Fourier transform? Fourier transform is actually transforming from time domain to frequency domain. Okay. So this is another way. Just we are seeing the signal in a different transform. That is we are doing the transformation from time domain to frequency domain. And here in Fourier series, we have different Fourier series, that is continuous time Fourier series, discrete time Fourier series, DTFT and DFT. Okay. Now, since we can write the periodic signal in the form of sum of sinusoids for using Fourier series, so we can use that in Fourier transform as well. Okay, for periodic signals only. So how we are using, I will tell you. So please don't get confused between Fourier series and Fourier transform. These are completely different. And yeah, so Fourier series, let's. I never forget these concepts because I have that logic in my mind. So I want to tell you that the same logic so that you also don't forget these things ever in your life. So this is the time domain representation. Remember, time domain of periodic signals. Okay. So since it is periodic signal, so it will be defined only for t. Period to t. It can be exponential form or sine cosine form. So exponential form is also sine cosine form because if you write e of x equals to sine of x plus j cos of x, right? And also we can write sine of x equals to e of j theta minus e of minus j theta divided by 2j, and cos of x equals to, sorry, cos of theta or x we can write here, x. E of jx plus e of minus jx divided by 2. Here j is here, here j is not there. Okay, so these are basic exponential to sine cosine. Okay, now what is Fourier series? So Fourier series is, we define this term c of c coefficient. Okay, c is nothing but 1 of t minus infinity to infinity minus infinity to infinity. Suppose we are writing time domain representation for x of t. Fourier series for x of t, where x of t is periodic signal. Okay, so x of t, I'm writing different color itself. C of k is equals to, it is defined for every k. C of k 1 upon t minus infinity to infinity x of t e to the power minus j 2 pi k f naught t dt. And x of t can be written as k is equals to minus infinity to infinity c of k e power j 2 by k f naught t. So this is the exponential way of writing Fourier series. Okay, where f naught is fundamental frequency equals to 1 by t. Okay, because we are writing in the harmonics of fundamental frequency. It is not equals to f by b, which is the harmonics of fundamental frequency. So that is what the Fourier series is written in harmonics of fundamental frequency. Okay, and t is time period because it is periodic signal. I hope this is clear. This is Fourier series, and you can convert this in the form of sine cosine also. But I can also write like this. This is a naught summation of ak cos 2 pi k f naught t k minus infinity to infinity plus k is equals to minus infinity to infinity pk cos 2 pi k f naught t, where it is here the k will be only even and here the k will be only odd. So you can check the actual formula, the basic formula which I remember. I can actually derive this, but we are running out of the time. So this is the basic formula, basic, and I also remember like this, and this is the correct one. I never forget this in my ever in my life. So this is the Fourier series formula. Now, what is Fourier transform? As I was telling. So since I was telling Fourier transform, what is that? Fourier transform. The only same thing is that the same scientist discovered Fourier series and Fourier transform. Otherwise, there is no similarity. This is transforming a time domain signal to a frequency domain signal. You're transforming itself. Like if you want to see some signal in the frequency domain, you want that. And why we want Fourier transform? Because the convolution in time domain is very difficult. And whereas the convolution becomes only the multiplication in the frequency domain, that's why you do Fourier transform. And also we want to see the spectrum. Like we are bandwidth hungry and we are running in that perspective where the spectrum is very important. We want to use the spectrum in the most popular way, most efficient way. That's why we are doing the resource allocation in a very efficient way. Okay, we want to have the more and more utilization of the spectrum that is given or allocated by the government or the US government, and the standard that maintains this spectrum allocation and all, it's a 3D and ITU. So that spectrum is given. So if you want to see the signal in the spectrum domain or want to find the bandwidth of a signal, then you do the Fourier transform. So that's why Fourier transform is important. Similarly, why Fourier series is important? If you want to convert or want to see the harmonics of one single fundamental frequency, okay, and we want to see the signal in a better way or more calculated way. If you convert it in sinusoid and non-sinusoid, it will be very important. It will be very easy to calculate it. So that's why you convert that periodic signal in the form of harmonics of its fundamental frequency. Okay. Now you have the different types of Fourier transform. If we see the basic Fourier transform, which is defined for the continuous time signal, so you will call it as CTFT, continuous time Fourier transform. Continuous time Fourier transform. So you have xt and you are transforming to capital of X of f. Now, this small xt and capital of X is different. Don't confuse with the simple X. Some people use the same X, but it is not because it is a transform. You can't use. Otherwise, you can have simple xt of cos 2 pi ft. Suppose cos xt, then small x of s cos of f. It is correct? No. So that's why if this is a different function itself, that's why the x of capital X is used. Okay. Now this is CTFT. So x of f is defined as minus infinity to infinity x of t e power minus j 2 pi f t dt. Now, the output of a continuous continuous time frequency transform is continuous itself. So if we do the x of t is equals to minus infinity to infinity, capital of x of f e power j 2 pi f t tf. Here plus sign is there. Or also, while calculating Fourier series coefficient, also here negative sign is there. There is fundamental difference between that. Please don't confuse. Here negative, here positive only. But here if you say this is negative, this is positive. Now, if you want to have x of omega, omega is what? 2 pi of f. So this x of omega is equals to minus infinity to infinity x of t e power minus j 2 pi f t dt. Same, but if you want to convert from x of t, so since f is equals omega is equals to 2 pi f, so since if you are having this particular thing, so you will have 1 upon 2 pi minus infinity to infinity x of capital omega e power j omega t or dt. Sorry, d omega. Or here you will can have j omega and I hope this is clear. This is CT, CTFT. And CTFT output क्या होता है? Input is and input is continuous and output is also continuous. Okay. Now, what if the output is discrete or input is discrete? What will happen in that case? So another type of Fourier transform comes into the picture. That is DTFT. That is discrete time Fourier transform. I'm a little bit rushing because I have to cover some 2-3 questions. But after this DTFT and FFT, I will just go to the questions. So yes, DTFT. So DTFT is defined for discrete time. So input is what? Discrete. But the strange part is output is continuous. Also, very, very important. In CTFT, input is discrete and aperiodic. And output is also continuous and aperiodic. Right. And this is discrete. Periodic. Continuous and aperiodic. Okay, let's see the examples. So since input is discrete, so x of n, so sorry, discrete and aperiodic, continuous and periodic. That is the difference in x dft. So here you will have x of f equals to x of n e to the power minus j 2 by n f or fn minus infinity to infinity. Okay, since output is periodic, so it will be the periodic with the period is 2 pi. Okay, so that's why x of n equals to, and since the output is continuous, minus infinity to infinity. So this you can write since it is continuous. So minus infinity to infinity. So since this is x n, sometimes I also get confused, but yeah, this is if this is n, so summation will come for sure. And these formulas are correct only. I'm damn sure about it. So x of n is nothing but minus infinity to infinity x of f. Why I'm taking minus infinity to infinity, I'm telling you that. So this is e power j 2 pi n. This is t. Oh, this is n dt. Why this is I'm taking minus infinity to infinity as integration only. Why? Because this output is continuous. You can't take the discrete function. Okay, but here the input is continuous discrete, so you have to take summation. Okay, so as also this is periodic in nature, so that's why 1 upon 2 pi will come into the picture. This is n you can take. This is what DTFT. And you remember, if the input is discrete and aperiodic, the output will be continuous and periodic at the same time. But if what is a DFT? If input is discrete and periodic, the output is also discrete and periodic. Okay. In that case, x of omega, sometimes we write not f or j omega we write, but that is fine. J omega is equals to n of minus infinity to infinity. But here, since this is periodic in nature, so here we can write x of n e power minus j 2 by k n, where k is equals to 0 to n minus 1, where n is period for n, because we don't need to differentiate over uh, all the elements. But now again, x of n is equals to 1 upon n. N is equals to 0 to capital N minus 1, because period will be same only. Capital X of k, here we define as k, capital K. This is e power t to pi kn. This is DFT. So what is the difference between FFT, DFT, FFT and DFT is just if we implement this particular formula in the form of butterfly structure to ease the complexity, then it is FFT. That's why it is called fast Fourier transform. But it is same for the DFT, whereas for DTFT and DFT's differences, like input is different. In case of DTFT, the input is aperiodic and discrete. Okay, but in case of DFT, the input is periodic and discrete. And output also is periodic and discrete. Whereas, whenever the input is discrete, the output will be periodic. So that's why these formula is used. Whereas in case of DFT, these formulas is used. So again, I'll give you this small, simple table. Input and output. If input is continuous and aperiodic, output is also continuous. This is Fourier transform. Fourier transform. Continuous and aperiodic. As input is discrete and aperiodic, this is CTFT. Aperiodic. Output is continuous and periodic. This is DTFT. If input is discrete and periodic, output is discrete and periodic. This is DFT, and FFT is nothing but fast form of DFT. Okay, and this particular thing, W, we can write this W is nothing but e power minus j 2 pi. Okay, so we can write WKN is equals to e power minus j 2 pi kn. So if we write x of k, so x of k is this one. Suppose x of capital 0 to x of n, because period is this x of n minus 1, it will be defined. And this is W1, W. This is 1000000. 1111111 W1, W2, W3. This is W2, W4, W6, like that. And this is x of 1, x of 2, x of n minus 1. This is DTFT. For similar way, if you want to have x of n, you can have W of minus 1, minus 2, like that. And 1 by n will be common here. And this is x of k. Now the one expression left, which is if we have continuous and periodic. So that will be solved actually using Fourier series, because Fourier series for any periodic signal we can write in the form of Fourier series. Okay, and for if we can write in the any signal in the form of Fourier series, so it will be very easy because all the sinusoid signals we know the Fourier transform that is in the form of impulse and non-impulse. That will be simple summation of impulse and non-impulse. So this is also very important. That we can write in the in using Fourier series, but Fourier series has no direct implications with the Fourier transform. Okay, now we will go to the questions that was there in week 3, sorry. So I covered Fourier series, Fourier transform very fast. So if you have any doubt, you can refer to my lecture again. And there are some lectures already posted in my YouTube channel in in signals and system. So that is very detailed. So this is very important. Fourier series, Fourier transform. What is the fundamental frequency and what is the basic principle that is driving, so that you will never forget ever in your life. Okay, and what is difference between convolution and correlation? This is the basic for signals and system. Okay, so okay. So the first question is FFT operation is computationally efficient or to compute what? The answer is DTFT, discrete time Fourier transform. It's just a way to compute or improve the frequency of discrete time Fourier transform. Okay. Answer is sorry, TTFT, no, sorry, TFT. So we saw CTFT, TTFT, and DFT. Okay, so DFT only because the input here was periodic and discrete. Okay, DFT. So sometimes, like I know, but still I got you. So answer is 4. Now, which of the following requires the least number of computations? Direct computation, FFT based computation, or overlap and or overlap save? What will you choose? FFT based computation obviously, because that's why we use that as a butterfly structure. We utilize that one. Okay, so that is very important. So you can see using the formula. This is this one, and if you used twiddle factor, this W was a twiddle factor, and you used the addition and multiplication of this twiddle factor in a proper way, so that makes the butterfly structure, and that is FFT. Okay, I never like learned this FFT, but yeah, the FFT structure is very important to understand. We have to find it in a butterfly structure so that it helps in calculation of W. So that's why it is computationally efficient. Okay. The event space of the discrete sample space is event space is what? Power set only. Sample space is here. Sample space is nothing with this one. Power set is 2 power sigma. This is what? Uh, all the possible subsets will be the power set of 2 pi sigma is nothing but all the subsets, all possible subsets of omega. So in the probability space, the event space is a collection of all possible events that can occur in a simple sample space. The event space is actually considered from the sample space, and the one common way is to define in the power set. So power set that is there. Now, the event A and B, E and F is mutually exclusive if we know that this is correct. This is correct? No. This is correct? No. This is correct? No. P of E union F should be P of E plus P of F. Okay. This is correct. This is one independent event. So only answer is second. Answer is second. Okay. The mean square value of a random variable having the mean u and mu and variance sigma square is what? The mean square value can be defined as E of x square. E of x square is actually mean square value. So what we define, first of all, let's say the nth moment. So nth moment of any random variable of any random variable is nothing but E of Oh, what I would have done. Oh, so defined as E of x minus mu power n. Okay. Now, if variance is defined, so variance is nothing but E of x minus mu power 2. So which is equals to E of x square minus mu square. Or mu is what? Mu is nothing but E of x. Okay. So it is asked, mean square value it is asked. So variance is given as sigma square. So E of x square is nothing but sigma square plus mu square. So answer will be 4. Answer is 4. I hope this is clear. This is the moment calculation using expectation of any random variable. So the commodity distribution function of a random variable is what? Continuous, right continuous, left continuous, or differentiable? So answer will be right continuous because it's only defined for right, and it is continuous also. Why it is continuous? It should be continuous in the sense that it is because you have to define that a PDF also. Then if it is not continuous, then you can't find the value of a PDF. The cumulative distribution function of a random variable is a function that gives a probability of a random variable is less than or equals to the specified value in mathematics. It is defined as this is one, and the is operation correct or incorrect. So it is continuous. It is continuous, not correct properly because it should be right continuous only. It is not necessarily continuous. It can be discontinuous various points because it has a discrete values in case for a discrete random variable. It is correct answer because the cumulative distribution function is right continuous, meaning that there is no jumps or abrupt changes. Okay. The probability density function for a random variable is positive, non-negative, or negative or non-positive. Should be non-negative because it can have the value for 0 also. Okay. Positive means it was only positive. That is not correct. Okay. Non-negative is answer. I hope it is clear why it is non-negative because it can have the value of 0 also. That's why it is non-negative. Uh, Now it is asked the eighth question. The expected value of a binary random variable that takes a value of 1 with probability 1, p, and 2 with the probability of 1 minus p. So what is the expected value of any random variable is defined as summation of our pi p of x of equals to xi. Okay, so what does this mean? Probability multiplied by, sorry, xi. Oh, xi. I so 0 to n or minus whatever the values is there. Or in continuous time, it is x fx dx. Okay, minus infinity to infinity. So this is discrete, so it's solid. This is 1 into p plus 2 into 1 minus p. So it is because this is the excise value of random variable. So p plus 2 minus 2p is equals to 2 minus p. So answer is 2 minus p. You can solve for any type of question, I guess. Correct? Okay. Okay. So finally, we have covered all the topics that was covered in week 3 and also the questions there in last assignments. So thank you so much for joining and thank you so much for staying till the last point. I don't know up to what point the points are clear or not, but still if you have any doubt, you can reach me via email that is given in the NPTEL portal, or you can also have any doubt. If you have doubt, you can ask here also in the chat box. So I think we can end the class today. Okay. Thank you so much for joining. Thank you, Malai Mata and Dishant. Uh, so I'm ending the class today. Yeah.